likelihood approach. Let's go to this idea of using projections to avoid the curse of dimensionality. I proposed yesterday to use this exercise. I don't know if somebody tried to do it, to know that, to check expectation of, so let's take z of x random that belongs to r times r cubed random vector, and then the expectation of that is, sorry, this is the integrity, and let's say the expectation of that is 0, to simplify things. Then your expectation of that given x is 0, and the second statement is expectation of that given all the linear combinations is 0 for n beta. Let's say of norm 1. This does not change too much. Fact. Have you tried to do it? So clearly 1 implies 2, yeah? Because expectation of z given x transpose beta is expectation of z given x transpose beta. Okay? And this is 0 by 1. Because this is 0. Of course, the other way around is more complicated. This is for A B. The other way around, we start with expectation of exponential I x transpose beta times expectation of z given x transpose beta. So if 2 is true, this is 0. Okay? Well, the trick, of course, when you see things like that, the first intuition that you should have is to go to characteristic functions. So this could be, of course, you may use other type of projections if you have something equivalent to the characteristic function. But this one is the most convenient, probably. And this is the same. So this is you can get inside. So it's got I x transpose beta z. Okay. And now you condition with respect to z. You get something like this. This is true for any beta. By 2. Well, I said beta of norm 1, but of course if you multiply beta by another number, non-unit number, then you get for any beta. This does not change anything. So what you obtain is 0. It is expectation of the exponential of I x transpose beta times this function. This is 0 for any beta. This will imply from the properties of the characteristic functions that this is 0. Almost sure. maybe you have, if you want, you have to split in two parts. It's positive part, negative part. You get two measures. If you don't agree, just directly like that. So this is a very simple remark, but that could be very useful in smoothing, because what this remark tells you is that if you want to check that this is 0, you don't have to smooth in the dimension of theta. It's enough to smooth in dimension 1. But of course you have to smooth for many, many directions, because this should be checked for all the directions. But now, of course, you said that here are statisticians and people coming from numerical analysis. So if you combine these two ideas, you may of course, what you do, you just look on the hypersphere, you look for an algorithm, and you just try to maximize on the hypersphere, and then you can check for all betas. Yeah? This is exactly what could, in this way, could happen. And at the present time, we would be very happy to have a nice algorithm to maximize on the hypersphere. Because, of course, you can of course understand what will follow, but we'll try to consider all these quantities, and we'll try to look in some way to all these betas. And for this, we have to, of course, we cannot look at all the betas on the sphere. We'll make a grid, and we'll look following a grid what the best or the worst of beta would be. So numerically speaking, there is some work to be done. And today we are doing in a very silly way. We just take a uniform on this hypersphere, and then we check for many, many points, but not for all of them. So this is very nice to understand that the condition that we had at the very beginning could be brought in a lower dimension space. Now the problem with this is for the null. What about the alternative? What about if this equality does not hold true? What will happen with these quantities? Is it true that all the betas will show you that this is not true? Probably not. How many betas will give you the wrong answer? How many betas will tell you that will give you the wrong answer to the question if this is equal or not? So there is a result that could be proved when X is bounded that says it's the following thing. If you imagine that you are under you don't have this equality. The expectation of Z given X equals 0 is strictly less than 1. Then let S be the set of all the beta such that this projection is 0. These betas will give you the wrong answer. These betas will be misleading for you because this is not true, but for this beta you get the answer that it is true. So these are the misleading beta. So what would you like to know is how many misleading betas you have when you are under the alternative. Fortunately, only few of them. So fortunately, there are very few betas that will give you the wrong answer. So in fact, it could be proved that it's only collections of contours and points on the sphere, not more than that. So if you select randomly a point on the sphere, the probability to pick up a misleading beta, if you are under the alternative, is 0. And it's even worse than that. It's even poorer than that, in some sense. Because it's only units of contours and points. Okay? With this at hand, we can reconsider the test procedure. So that is why we call this breaking the curse of dimensionality, because we will no longer smooth in the dimension of X. We will smooth in dimension 1, using this idea.
So from here, From here we cannot say that we can test for smallest, for a subset of the unit sphere yet from this B statement.
We can take only a part of the hypersphere as long as this part is of Lebesgue measure, strictly positive Lebesgue measure. And we still get the good answer. You are not forced to take all the sphere.
That's enough. Any positive Lebesgue measure will have a consistent test.
You get a consistent test due to point B. Okay?
And in this paper, do they have a proof? I mean, is it included in the paper? A proof of this theorem?
Yeah. Well, Bjerre's did not do it in this way. We used the Bjerre's result and we put it in this way. So, with this in mind, let's go back to the testing procedure to see how. Let's fix the ideas. Let's say that we are testing regressions, mean regressions. So then, the idea would be to rewrite the H0 hypothesis under this form, and then to, of course, use the idea 1b and to rewrite everything under this form. So here, now, we no longer need the density of x, we need the density of x beta. So, of course, this is a univariate density. But then the idea would be to consider a criteria of this kind that would be positive all the time for any theta and beta, and that would be, we could also integrate all this with respect to beta on the sphere. The uniform law on the sphere, it's obtained if you want to generate a uniform random variable on the sphere. The usual way is to take a Gaussian vector with identity variance matrix and then to normalize the vector. What you obtain will be a uniform on the sphere. Okay? So you can also integrate this with respect to this uniform law on the sphere, and you can have two approaches. One is of Kolmogorov-Smirnov type. You just look at the maximum of this Q quantity with respect to B. It's like looking for the worst direction on the sphere. This is the spirit of Kolmogorov-Smirnov. The other one would be, as I said, to integrate everything and to look on the whole sphere, or at least on a subset of that. And this is what we call the integrated test. Well, I will get more into the details in the integrated test. Argmax test. The integrated test has some problems. So we define an estimator of this Q theta beta quantity, of course, like we did previously with this quadratic form. The same ideas we used previously, we applied it right now for any beta. It is exactly the same idea. But right now, the big difference in some sense is that here you don't smooth in Q dimension, you smooth only in one dimension. So here you just divide by h to the power 1, instead of dividing by h to the power q. As previously, epsilon is a residual in the model and kh is k over h. And theta n is an estimator of theta naught. Theta n is not appearing inside. I don't know what I call it. So, this is exactly the same like before. In some sense, it's nothing new. Only this idea that you smooth in one dimension by doing projections. So if we maximize the quadratic form with respect to beta, intuitively what will happen? If H naught does not hold, what will happen with this quadratic form? If H naught does not hold, there will be at least one beta, at least one, in the domain we are considering. Let's say that we take the whole hypersphere, or only a part of it. Only a part, that is of course of positive Lebesgue measure. If you take something that is negligible, then maybe you have problems with that. So then in this set it will be at least one beta that will make this not to be 0. And if this is not 0, the limit of the Q will not, this will be strictly positive. Because there is at least one that makes this strictly positive. And then, since this is strictly positive, the empirical counterpart of this should stay away from 0. Should no longer converge to 0, if you're under this limit. The problem is, now, there is no problem. It could work in this way, no problem. So one possibility would be to try to study this process, that is a process with respect to beta, and try to understand what the behavior of this process is under the null hypothesis, and try to derive some critical values. This would be a very simple way to proceed. The big problem would be that the Qn, which is, remember, a U process, U statistics of order 2, our impression is it behaves very erratically. It would be rather difficult to understand what the limit of this process is with respect to beta. So, there are two possibilities, at least two. Either you get very strong and very nice probabilistic results about the convergence of this process with respect to beta. If you are able to do that, then hopefully you will be able to say something about the limit of the maximum, and then you are done. You have something to test. Without any doubt, the limit will be quite complicated. No way to get something that is nicely defined in tables, things like that. No way. This would be no hope. But if you don't have such probabilistic result, and we do not have today, and we know to look for, because it seems really very difficult, and life is so short, maybe somebody else will find it.
Give it as exercise.
Sorry? Yeah. Exercise for tomorrow, yeah. Exercise for tomorrow. Well, what is very funny, it's that for a fixed beta, the central limit theorem tells you that this goes to a Gaussian. So for fixed beta, you know how it behaves. But as a process, we fail to prove tightness and things like that. Maybe we are not sufficiently skillful for it. But then you will use a trick, as usually.
Can you tell just maybe one more sentence? What is the problem of
The tightness.
why the usual stuff?
The tightness.
The
The Philly distributions, the finite dimension distributions, you get the Gaussian.
yeah.
Very correlated maybe, but at the tightness we were not. I don't know if it's tight. I don't know. I think it is not, in fact. So we try to do some pictures of this process. It's very regular. We cannot understand what is the behavior of this process. Maybe some probability. We asked this question to people working with U processes, and we were not able to tell. Maybe they didn't want to look in this problem.
Basically, if you show it again, this just the sum. So I mean, you want to understand the behavior in beta.
Yes.
Basically, if you center and
Everything is centered. Imagine that This is center, this is center.
Basically, you have to bound the local deviation in theta and
In beta. In beta.
and in beta. So what would damage if you just take the random process and take the supreme over theta and beta at the same time?
Well, theta, you can forget it. Theta is not important. Theta could be theta naught. If we know how to do it, because the difference between theta and theta naught is much smaller than the increments of this process. So let's forget about theta. Theta is not here. It's only beta. But the problem is how to control the difference between two points beta. This was the problem we felt.
Okay, so it's exercise for money.
Exactly.
I don't understand actually, but no, we did it for one dimension. So maybe for many dimensions.
For one dimension?
Yes. For local deviation.
You mean for h? Because this is like doing for h. Would you be able to do as a process in h?
No, it's not a story, but it's more or less the same. Process in H and process in beta, because the derivative would be at the same time. Oh, okay, so this is a great
Okay, please. I would like to, yeah.
to think about.
I would be really happy to have some hints about how this process behaves. Not necessarily for testing purposes, but later could be very interesting for other purposes. So, since we don't, we do not want to work with this supremum of this process that seems to be a bit complicated, we will use a trick that is the following. Let's take here, inflate by this number nh to the power 1/2, which should be the rate of convergence of Qn under the knob. Okay, this is a normalizing factor to get the central limit theorem, because we are smoothing in one dimension, and if you remember, the normalizing factor was nh to the power q over 2. Previously, now we are in one dimension, so it's nh to the power 1/2. Okay? And then let's put here a penalty with some beta naught, a direction, a privileged direction that you believe that is gives you some power. You are interested in being powerful against this direction. For instance, you would like to take beta to be only 1, 0, 0, 0, 0, and you select only the first variable, for instance. You would like to be very powerful against alternative depending on the first variable. And then, of course, this penalty, what is the role this penalty should play? What would you like this penalty to do? Under H now, if you take alpha n suitably, in some sense, to be larger than the increment of the first part, what will happen? Under the null hypothesis, this will be bounded in probability, okay, because this will go to some sorry, this is bounded in probability. Here is not beta naught, sorry, here is beta, not beta naught. So if you take alpha to be not bounded, sorry, alpha to be larger than the rate of this process, then in the optimization, what beta you will choose? If alpha n is larger than this part, then you would like to cancel this. And to cancel this, you take beta to be equal to beta 0. Okay? And this is what you'd like to happen under the knot. Why? Because if you take beta 0, you select beta 0, what we'll do next is to take this direction beta hat n, and we put it in the quadratic form. And if you take it to be exactly beta 0, then you come back to not to a process, but just to one random variable. And this you know how it works by the central limit theorem. This is under the knob. What would you like to happen under the alternative? Under the alternative, it is very likely that other directions than beta 0 may be better to tell you that you are under the alternative, may better reveal the failure of the H naught. So what would you like to happen is that under alternative, this part should be larger. Okay? So if this part is larger, you don't have to take alpha n too big. Because if this part is larger, then you will select a beta that maximizes this part, and this beta would be the best suited to tell you H0 is not true. Okay? So by this penalty trick with beta naught, a fixed direction, under the null you get the beta naught, and you apply the statistics for beta naught, and under the alternative you select another direction, and you will see very well this alternative. What is the advantage of that? Is that under the null you treat one statistic, not a process. This would make everything much easier. So on one hand you need it larger, on the other hand you need it slower. So there is a trade-off. Let's take Vn squared beta to be an estimator of the asymptotic variance of this quantity. And then we can define the test statistic to be the quadratic form in the optimal direction divided by the variance. And for the variance we can take one estimate or two estimates if we want to increase power in some sense, because it takes the minimum of two. Under the null hypothesis, the two standard deviation estimates will estimate the same quantity. Then the test would be, if this Tn is larger than the quantity of the normal distribution, then you reject the null hypothesis. So we avoid working with this penalty trick, we avoid working with the process. We just work with one direction. And why this happens in this way? Well, there are some conditions, some moments, some conditions here. I don't know. It's very interesting. Some moments on the epsilons, some boundless condition for the densities. Most of them are probably not necessary, just to reduce complexity.
Is it 11 degree?
Sorry?
Is it degree 11?
Yeah, this is to get some bounds for the process, to control the tails. Well, when we're looking, if you want something else, put something else. Right? If you put an exponential like no problem. So why 11? In fact, what we used, we can put here less than 11, but probably we pay a price at another point. So we have to control the increments of the U process. And for this we are using some exponential inequalities. Unfortunately, the existing results are given for bounded random variables. So we have to truncate it, and then we have to control the tails. And we control the tails by some moment conditions. And 11 comes naturally. This is a variance. Well, for the variance estimator, either we use this more interesting, because you had an exercise for today to see that this is more interesting than taking the squares of the epsilons. And if you get some non-parametric estimate of sigma, you plug it in here and you get a consistent estimate of this condition of variance. Well, probably you will not be very happy with that, because in some sense you say, look, you tried to avoid smoothing in Q dimensions. And now what you are telling us is that we have to smooth in Q dimensions for the variance. So you may not be happy about that. Well, the price is not the same. Here, all what you need here is consistency. Consistency. When smoothing in the test statistics in modern consistency, you need also to check for the rates. So here the price to smooth in higher dimension is a bit lower. But of course you may not be happy with this, and you may try to use some projections here too. For instance, to take here the conditional variance of epsilon given x beta 0, for instance. Why not? But this would be a trade-off between taking epsilon squared or taking this non-trigonometric here. There is no mystery in life. You have to pay a price always. So here we use epsilon to the power 11, or expectation, to derive this rate. So the process, the quadratic form behaves like the rate 1 over n h to the power 1/2, and the fact that you take supremum over all the betas, you pay this log factor. Okay? So once you understood this, you understand that alpha n should go to infinity faster than log n. Because if it goes faster than log n, remember what I said, if it goes faster than log n, then so if this behaves more like log n, and this goes faster than log n, it's exactly the condition we wanted here. Okay, so now we understand how fast alpha n should go. And log n would be a kind of minimal rate to diverge. So it could be proved, and this could be a very simple exercise. I don't know if you saw on the slide. Otherwise, it could be proved very easily that if alpha n goes to 0 and then the beta hat n will be equal to beta naught with probability converging to 1. So this is exactly what we expected. If we penalize sufficiently hard, then what you will select under the null is beta naught. Okay? So then under the assumptions, you get with a test that is of asymptotic level alpha, if you compare with the quantile of the Gaussian 1 minus alpha. And then, as previously, what we will do is to look at some bootstrap approximations of the critical values. Of course, here the problem is more complicated than it was previously because we also have this alpha factor, and without bootstrap, we are pretty bad in shape. So we need to bootstrap also because of this alpha, because the effect of alpha n theoretically, once you take it to be faster to infinity than log n, then you have no problem. But in practice, you know how alpha n should be. 3, 5, 10, 11, 250, all of this can be faster than log n rate because it's not no constant in the story. So. Well, let's try to understand why the test is consistent against any fixed alternative. So, by definition, the test statistics is larger than if you take the variance here to be beta naught, because we took the minimum between two variances. And then, also by definition, this would be larger than this. Oh, sorry. You put here this, and you deduce this here, and you put it here. Then you drop this quantity, which is larger or equal than 0, and you come with this. And then, here it's a maximum, and what you do is to say, among all these betas on the sphere, there is at least one, such that this Qn, without the normalizing factor, will converge to a positive constant. So pick up such beta. Then you have this inequality, and what will happen here this will go to a positive constant. Here you have an inflating factor. Everything goes to infinity. Its alpha n is not too big, is what we asked. It's grow to infinity, but not too fast. Then all this will explode to infinity. So now here you understand why alpha should not be very fast to infinity, because then maybe it will compete with this quantity that increases to infinity. So it should be as small as possible, but faster than log n. Okay? That's why it would really be consistent for any fixed alternative. Fixed, but you can also understand immediately what will happen when you have alternative approaching to zero, because what will happen with alternative approaching to zero, this will increase to infinity, but slower, of course. And then you understand immediately how fast can you converge to zero, the alternatives, in such a way that this is still larger than alpha n. This is the price you pay with alpha n. That's the only price for power. So the test is consistent against fixed alternatives. And as I announced already, if you consider, look, this condition is the fact that delta is orthogonal on the model. We talked about that. But the expectation between delta and the gradient of m ensures you that you are outside the model, you're not moving inside the model. So you focus on the properties of the test, and you are not concerned of what happens that you're estimating some other parameter in the model. You're always estimating it or not. So if you take alternatives that are of this kind, these Pitman type alternatives with a decreasing rate of Rn, then if Rn is satisfying this condition, then you may detect it with this test. And, well, for Q regressors, sorry, I changed this for P. With Q regressors, well, the condition you ask is Rn n to the power h to Q over 2 goes to infinity. So you see that with this type of, you don't lose any power. You don't have the exponent here increasing when the sample size, when the dimension of the covariate is larger. This is theoretical, of course. This is in theory. But we tried it in practice, and with dimensions with, let's say, 4 or 5 regressors, the test really behaved nicely compared with the test that's smoothing 4 or 5 dimensions. It was really powerful. The results were much better and very close to a kind of optimum, because we knew the alternative, so it was possible to see what would be the best test in some sense, and we found very nice results in simulations. Right? So we broke the curse of dimensionality. Here is a curse. There is no code here. That is. Well, you may ask what happens if you try to look at this Minimax story about alternatives, where it was written some moment here. Well, delta n is allowed to move. It's not the same. The direction is not the same. You can change it. And in fact, as expected, the test will behave quite nicely if the alternatives are in a class of functions, Sobolev, Besov, or whatever you may choose from the theory Vladimir developed with other people. As far as you take functions delta with certain regularity, and these functions depend only on some index, it's clear that you will be almost optimal. Because the philosophy of the test is to project and then to look at, in some sense, to all the directions and to detect like you are in the one dimension. If your alternative is of such nature that depends only on one index, even if you don't know it, you don't care, because since you look at all indices, at some moment you'll detect it, and you go optimally in that direction. So of course we cannot be we cannot be optimal against all the alternatives. There is no mystery. We are smoothing in one dimension, we could not beat the minimax theory. But what could we do? We can detect special types of alternatives, those that are depending only on index. So this is exactly what, well, there are some technicalities about the design. The design is also always a problem. Well, we could suppose that the design is fixed and it's irregular, otherwise you have some conditions, bizarre conditions, but without that you cannot solve the problem. What he's saying more or less is this result is that we will be able to detect alternatives that approach zero at almost the optimal rate. This result is stated with the regularity is known. Okay? S is known.
S is
The regularity of the class.
okay.
So if the regularity of the class is S, then you get this result. And the only difference you see with respect to previous work on this type of test is this alpha n factor that appears here, the price we pay. So of course, the optimal value then that will allow to achieve this optimal convergence will be of this order. So for alpha, you may put a logarithm or something like that. But if you don't know S, then you have to use some adaptive procedures and go back to this maximum on a grid scheme that was developed. Things should behave in the same way. But of course, this is only if the alternative behaves of some index that is not changing with, well, is not changing with n. Oh, could it change with n? No, probably not. No, I have to think. I have an exercise. Okay. So if it's not changing, it's okay, but maybe we can change it.
So other alternatives, other novel alternatives,
Sorry?
you can't detect if it's not single index alternative, local.
Of course we can, but we will not have the same rates, minimax rates. We may detect all the alternatives, it's omnibus, approaching zero, but we do not study the rates for a general type of alternative because it's for sure will not be optimal. The test will not be optimal. We are not smoothing in all directions, so you cannot detect at the optimal rate the rates that was established previously on the previous slide. You cannot, with one test using projections, you will not be able to see at the same rate. You see it, but at a suboptimal rate.
We don't have bound, so we can say if the alternative is this Rn multiplied by delta x, so what should be Rn? How fast?
Well, if you look at Piedmont's alternative, then the answer is clear. It was here. Piedmont alternatives are detected. Whatever delta is this is the only condition.
Okay, you improve the rates.
Of course, because usually you have q over 2 here. Well, it changes to p. It's q over 2.
Okay.
But this is only Piedmont. Then we wanted to look at uniform classes of delta, not only one delta. And we understood quite easily that we will never be rate optimal against general classes of delta. But we realized that we could be optimal in classes of delta depending only on an index. This type of classes, where the variable is x times an index. And then you put this in a delta, it's in a space, in a class of regularity, univariate class of regularity S. And then if this is the type of alternative, you may let this depend on n, of course, in this class. For instance, imagine that your alternative depends only on the first variable. Then you are optimal, you have the optimal rates if in this class of regularity depending only on the first variable, up to some factor log. that is given by alpha. This is the price we pay. Okay? Okay, so all this story is about testing. I wanted to show you some ideas about testing in parametric models. We also talked about how to test significance in non-parametric regression. And then we discussed several aspects. At the beginning of my talk yesterday, I told you that if you go a step further, you may also try to check single index models against several multi-index models using the same type of ideas. This is methodology, general methodology, but of course then in particular cases you should take care about all this approximation of epsilon and to control this difference between epsilon hat and epsilon, and you may come up with tests for all these cases I mentioned in the beginning. But the work is, of course, all the time the work will be when you are in non-parametric framework to control this difference epsilon hat minus epsilon. And epsilon hat minus epsilon will mean to control U statistics and the orders of several tens of U statistics, and to understand how that these are negligible with respect to a dominating term that will give you the central limit theorem, and then to give you the test. So all these facts, if you want, are quite useful in many situations. It's quite classical in some sense. It's quite problems that were solved already a few years ago. Now I'll try to put this methodology in a new context that would be functional data. So imagine it's very surprisingly, it will work very similar for infinite dimension covariates, the so-called functional data problem. So imagine that you have independent copies of two random variables, right now taking values in some functional spaces. To make simple, let's say that in Taylor spaces, let's say that either one is the real line and the other one is L201, and or both of them are L201. Well, it's a very much. It becomes of very much interest, the analysis of functional data, because a lot of data people register are of functional nature. I said yesterday, for instance, in medical applications, you have the activity of the brain, you have the activity of the heart that you follow over the day. On the market, you look at some curves. The stock price, you look at traffic or whatever you would like. Many times in statistical applications, you have data that are, in fact, almost recorded in continuous time. If you are not recording in continuous time, are repeated measures of the same process, and then instead of dealing with the whole data, what you would like to do is to smooth all these points and to get a curve. In this case, you summarize all the data points by a curve. And one more time you get with some functional covariate. You may also have functional responses. And the idea then people developed is to transpose the usual statistical, classical statistical analysis to functional data. Well, it's not very complicated, because imagine that you have in some sense it's very easy. Imagine that you have a basis in the L2, okay. And then your function, these are functions, orthonormal functions, and then a covariate x would be decomposed very easily in this basis, where xk is nothing but a projection of this element. Okay? So, once you understood this, is the information, so the information carried is the information given by x1, x2, and so on. If you have all these coefficients, you know everything about x. Okay? So what people usually do, of course, it's very nice because I say, even if you have repeated measures in time, you fit a curve and finally you get a curve, but at the end of the day you cannot work with the curve. What you will work with, it's exactly this coefficient small x. Okay? But this is usually, things happens, you have repeated measures, not necessarily at the same time, you fit a curve, and then you only uniformize in some sense your data, and then you take every curve and decompose in the basis, and you get this axis for every curve. This is usually people do with, in medical applications and other type of applications. Engineering, speech recognition, or whatever. Of course, that you will not be able to work with all the coordinates, and at some point you have to stop somewhere, and you do statistical inference using only a finite number of coordinates. So in some sense, if you want to give a quick judgment of what is functional data analysis, it's just multivariate analysis where the number of covariates and parameters are growing to infinity. That's it. It's nothing new on the Earth. Or under the sun, how do you say? So, it is exactly the idea that will, especially if you have a leader like Vladimir, who the sample size is fixed and you don't move it. So, oh, I disturbed it. So, it is exactly the story, and this is a way people put in place models for functional data. You take linear models, or generalized linear models, regression models in general, quantile models, whatever, and you transpose everything in functional data, using the idea that for sample size, the number of parameters and the number of covariates grows, depend on the sample size. Now, once you get regression models, the problem would be to check them. Are these models correct or not? So you understood immediately that what I will try to do is to adapt this theory that was proposed previously to the case where the number of parameters and the number of covariates grows to infinity. And I was still have an asymptotic approach to this problem that, to my very big surprise, it was an open problem. So for the moment there is no answer to this problem in functional data. So the variable u could be observed or estimated from some model. U could be a residual. And then what we would like to test is expectation of u given x is 0, almost surely or not. But or not in the sense no parametrics, so you don't specify an alternative. Fisher type tests are already proposed in several years, but as I said in the first lecture, Fisher type tests are tests against extended linear alternatives. So these are not could miss, and we show that they miss other type of alternatives, like for instance quadratic alternatives. So if you want to be non-parametric, you should proceed in a different way. And what is very funny, at the time we developed this test 5 months ago with a student, at the same time some Spanish team developed the empirical process approach for the same problem. It was very funny. They don't have proofs. If I have some time tomorrow, I'll try to convince you that probably they will never have proofs, because the empirical process approach is very likely will fail in this approach because of the fact that it depends on how you estimate the parameter. The law of the empirical process depends on how you estimate the parameter. When you are in a finite dimensional setup, no problem. But in the functional setup, the parameter rate of estimation depends on many, many things. There's the regularity of the parameter, the regularity of the covariate, and put all this together, they will never succeed. But you'll see that here is, of course I'm joking, I wish them to succeed, but it will be a much, much harder problem. And what is a pity is that the leading term in the empirical process approach, the leading term will be given by the estimation error for the parameter. And this is really a pity, because the test is driven by the way you estimate the parameter, which will not be the case with the smoothing. You hide this in the bandwidth, and we don't see it.
What is it?
Gonzalez Manteiga and some students. And they don't have theory for it. And tomorrow I will show you, it works pretty nice, it's very, very nice. Very funny. So, well, it's 7:30, just to put the problem, and then we'll go to it. So, testing parametric. Parametric, why parametric? Because even if you are in a functional setup, so infinite dimension objects, for me this is, I mean, not only for me, this is a parametric model, it's a linear model. Just have a coefficient, it's a function model. And here you have a constant. Yeah? So usual models developed and very, very much used in, you go in statistical conferences, applied or theoretical, you have at least 2-3 sessions on functional data. People are getting very excited on this type of models. And they're always talking almost about the same thing, but they have a lot of applications. And for instance, the functional generalized linear models are perhaps the most used, together with the quantiles are actually the only ones. And in these models you have this linear factor that's in the link function that is given, even is an identity or a logit or whatever, if you want, like in the finite dimensional case. So the model is correct if and only if the expectation of u given x is 0. Of course, u could be functional, maybe not with g or this one, but could be also functional. And it's very funny, this was a completely open problem even for the Spanish group. They don't know how to do it when u is functional. Imagine that u is some image and x is some curve, and there is a relationship between the curve and the image, and you define a relationship and you like to test this relationship. U could be also, remember, could be also functional. Other type of models that are very much used is the so-called quadratic models. In the quadratic model you have a quadratic term that is in the functional setup is written under this way. Then the unknown quantities to be estimated is this constant, this function, and this bivariate function. And again, the functional quadratic model is correct if and only if. How people usually estimate this? It's very simple. As I said, you decompose in the basis, you decompose everything in the basis, and finally what you are looking for are just some coefficients. It's like in the linear or quadratic nonlinear models. There is no mystery. This is exactly the way they are dealing with the estimation part. Okay? From the estimation point of view, it's not a problem. Of course, then you have to choose at which moment you cut your basis. And this is, of course, a very hard problem. You have to choose it in an appropriate way, if possible, data-driven. But we do not have to estimate. So, okay. Another problem that could be interesting to know about. In some applications you have, for some responses, you have hybrid covariates. So finite dimension and non-finite. Imagine that you have you are studying the heart activity of somebody, and together with a curve of the activity, you have the weight of the person, the gender, and whatever, the age, and so you combine the curve with some finite dimension. So you would like to write a model. So a very simple model would be to say something linear with respect to the parameter, to the finite dimensional regression, and then to put some function of the function. And before doing this, which was already done in some work, before doing this, it would be nice to understand if it really depends on this x, because there is a price to pay on this x. So you take this constant, you put everything on the other side, and you check if all this is 0. This is another problem that we could answer in such kind of model. All this is in the setup of... Okay, so we'll stop here, the exercise for tomorrow. It's the same projectional lemma, but now it's for any p. Now it's for any p. Now it's for any p. So this is the exercise for tomorrow. You have it on the web, yes? Slide 74.
I hope so. This I transferred it to principal people which should check whether it's on the side. Okay, so it's done for today, yeah?
Let's stop here. Thank you very much.
Thank you.